We finally come to the point where I want us to close this discussion on the LU factorization with the situation when a matrix A requires row exchanges to be able to reach that upper triangular matrix U. No matter how the start of the matrix looks like, so you may start with a matrix A where it is not obvious that you need to do row exchanges, and then after you carry out the first elimination, you realize that some rows need to be exchanged. Well, whenever you come to discover this need for exchange, the point is that the exchange can really be carried out in advance. So you could start with a matrix where before you begin the elimination, you rearrange the rows in a way that you actually need. Now, let's look at this on an example because this factorization is not too important. It just closes the discussion on all matrices that don't have LU decomposition. The only reason they wouldn't have it is because they require a rearrangement of the rows. Really, we will be focusing on matrices A that already have their rows in the proper form, but we just need to know how to work with this as well. So here we look at the matrix A that I have written here, and in the pivot position, we have a 0. That's not allowed. We can't eliminate with 0 because, well, we don't have that variable there. We don't have that coefficient. So we need to do a row exchange. We can do a row exchange between the first and second or the first and third. I personally like to have a 1 in my pivot position. So I'm going to exchange the first row with the second row. And remember, this type of operation gives us a permutation matrix. This is not an elimination matrix. This is a permutation matrix. So once we have carried out that row exchange, we have 1, 2, 1, 0, 1, 1, 2, 7, 9. And now we can carry out elimination in a normal fashion. We eliminate with the first row. There is nothing to be done in the second row, so we just eliminate in the third. We have R3 minus 2R1 into R3. We get 1, 2, 1, 0, 1, 1. Then 2 minus 2 is 0. 7 minus 4 is 3. 9 minus 2 is 7. Then we go to the second pivot in the second row, second column. We eliminate underneath. The operation is R3 minus 2R2 into R3. And we get the matrix 1, 2, 1, 0, 1, 1, 0, 0. And then, oh, sorry, I have a mistake here. This should be a 3 minus 3R2. And here I have 7 minus 3 is a 4. This is the matrix U. I'm going to push this up. And now I can write the reverse operations to help me find L. So the inverse here is R3 plus 3R2 into R3. The inverse here is R3 plus 2R1 into R3. And I actually don't want to change, I don't want the inverse of the permutation because I want to apply the permutation onto A. So actually this matrix over here is PA, and L is supposed to take me now from U to PA. By the way, the matrix P in question is just apply that operation R1 exchanges with R2 onto the identity matrix, and what you will get is 1, 0, 0, 1. So the first and second row of the identity matrix are exchanged. This over here, remember, was the matrix A. Now let's write that L matrix right away without using the identity matrix. And that is absolutely possible. So what we know is that the matrix L will be lower triangular with ones along the diagonal. And then we need to fill out the 3 spots under the diagonal, because above the diagonal we definitely have zeros. You can go backward, you can go forward, it doesn't matter too much. Just focus on the following. So in the first elimination step, which is right over here, we eliminated this entry. So that entry needs to be filled out here. Because we already had a 0, we are not going to have anything non-zero in L in that position. So I know I have a 0 here because there was a 0 in PA, so I didn't need to eliminate. And then the 2 goes right here. Then from the next step of elimination, which is represented by this operation, I eliminated right here. The number that I need to write is that 3. So what I have is a 3. So I know L right away, just I can read it off of the elimination steps. So finally, what I have is that the matrix PA, so 0, 1, 0, 1, 0, 0, 0, 0, 1, times the matrix 0, 1, 1, 1, 2, 1, 2, 7, 9. Remember, that gives me this matrix over here, equals L, which is 1, 1, 1, 2, 3, times 1, 2, 1, 1, 1, and the 4, remembering that everything I have not written is a 0. So we have PA equals LU. So this is just to complete our understanding of the LU factorization of a matrix, that sometimes we may need to exchange rows in advance, and then we can carry out this LU decomposition.